Hello everyone, this is another video. In this video, I'll be discussing previous year questions of JEST from atomic and molecular physics, right? And in upcoming days, we'll be solving previous year questions of JEST. JEST is coming up. It's on March 3, right? JEST is on March 3, so we better start our preparation for this. Hmm. Yeah. So in this class, I'll be discussing PYQs of JEST PYQs of uh, atomic and molecular physics, which is one of the easier topics in JEST. So let's start from here. Smart fetching, easy. In this video, I'll be doing from 2012 and 2019, and the rest I will do solve in another video. Okay. Okay. Let's start. Uh, question number one. Question number one is from JEST 2012. The binding energy. The binding energy of the hydrogen atom. Binding energy of the hydrogen atom, which is electron bound to proton. Binding energy of hydrogen atom is 13.6 electron volt. Okay. The binding energy of positronium will be binding energy of positronium will be dash. Okay, which is positronium is what? Electron bound to positron. Positron is the antiparticle of electron. Okay, will be dash. Okay, so the options are 13.6 by 2 electron volt. Option B, 13.6 by 1810 electron volt. Option C, 13.6 into 1810 electron volt. Option D, 13.6 into 2 electron volt. Okay, this came in JEST 2012. Okay, binding energy of the hydrogen atom is 13.6 electron volt. The binding energy of the positronium will be, all right. So let's you take your time, try to solve it first, then I will solve it. You can pause the video if you want. Okay, so read the question first. So binding energy of E and S. Positronium will be what? Minus 13.6 by m square mu by me, where me is the mass of electron and mu is the reduced mass of the atom. The reduced mass of the atom. It's a positonium. Positonium. Positonium is, what is positonium? Electron bound to a positron. Here electron is bound to a positron. Electron is bound to a positron. So here mu will be what? And see, electron positron is particles and antiparticle of each other, so their masses will be same. So me into me divided by me plus me, isn't it? Because their masses are same. So me square by 2 me, that gives me me by 2. Okay, that gives me me by 2. So I will just put it here, minus 13.6 n square. Okay, n square. So n square into me by 2 whole divided by me. Alright. So that will give me minus 13.6 n square into 1 by 2. Isn't it? So the binding energy. Alright. So I will just put n is equal to 1. That will give me the binding energy. E n dash is equal to minus 13.6 by 2. And we have to write the energy in positive. Okay. So the answer will be what? Answer will be 13.6 by 2 ev. Okay, which is our option? Option A. Alright, easy question. Hmm? Easy question. Yeah. Next question, write down. Question number 2. Question number 2. A sodium atom in first excited the first excited 3p states 3p state has a lifetime of lifetime of 16 nanosecond for decaying 16 nanosecond for decaying to the ground decaying to the ground 3s state. Okay, the wavelength of the wavelength of the emitted the wavelength of the emitted photon the wavelength of the emitted photon is 589 nanometer. Okay, the corresponding line width corresponding line width of the transition corresponding line width of the transition in units of frequency units of frequency is, okay, option A 1.7 into 10 to the power 6 hertz, 1 into 10 to the power 7 hertz, so see 6.3 into 10 to the power 7 hertz, and option D 5 into 10 to the power 14 hertz. This question came in JEST 2013. A sodium atom in the first excited state 3p state has a lifetime of 16 nanosecond for decaying to the ground 3s state. Okay, lifetime, that means your what is given, del t is given. Del t is 16 nanosecond. The wavelength of the emitted photon wavelength is 589 nanometer. Okay, yeah. So the corresponding line width in terms of frequency, line width, that means del nu we have to find. Okay, del nu. All right. So here, see, here how will we do it? See, we know Heisenberg's uncertainty principle. Del E into del T is equal to H cross, right? Yeah. Del E can be written as H del nu, right? To del T is equal to H cross. Is that all right? Hmm. So you can like approximately you can cancel them. Okay, you can cancel each other approximately. So del nu can be written as 1 by del T, as simple as that. Okay, so 1 by del T. Del T is what? 16 into 10 to the power minus 9. Okay, so if you do it, you will get it as 6.25 into 10 to the power minus 7 hertz. Sorry, 10 to the power 7 hertz. Sorry, which is almost equal to what? 6.3 into 10 to the power 7 hertz. So to be honest, like we didn't even need this equation, Heisenberg equation. We can just frequency is equal to 1 by time. So that way also, if you can do it, that's also easy. Okay, again an easy question. All right, this question came in just 2013. Right. Okay, next question. Question number 3. If a proton were, just a second. If a proton were 10 times 10 times the what? 10 times the mass of electron. Okay. If the proton were at 10 times the mass of electron, if proton were at 10 times the mass of electron, the ground state energy the state energy ground state energy of the electron in a hydrogen atom will be in a hydrogen atom would be option A less, option B more, option C the same, option D less, more, or equal depending on the electronic mass. Depending on mass of electron. If a proton were 10 times the mass of electron, the ground state energy of the electron in a hydrogen atom would be. Again, same thing. See, En dash is equal to minus 13.6 n square mu by me. What is mu? The this system 10 times the mass of electron into mass of electron divided by 10 me plus me, right? Because proton is 10 me. So this is 10 me square by 11 me, which is actually 10 me by 11. Okay, so you just have to put it here minus 13.6, and this is the ground state energy we need to find. Ground state means 1 into 10 me by 11. Me is there, me cancel. So minus 13.6, 10 by 11 is how much? 0.9995. Okay, so if you put it here you will get minus 13.59932, something like that. So yeah, so the ground state energy is what? Is it more or less? It's actually more. Minus 13.6, this is minus 13.599. So this is actually more, isn't it? In negative terms, right? So the answer will be more. Yeah. So this is question number 3. Question number 4. And the value of elastic constant for copper. Elastic constant for copper for copper is about 100 Newton per meter, and the atomic spacing is 0.256 nanometer. What is the amplitude of the vibration? What is the amplitude of the vibration of the Cu atoms at 300 Kelvin as a percentage of the equilibrium separation, as a percentage of the equilibrium separation. Okay, Options are 4.55%. Option B. Option B 3.55%. Option C 2.55%. And option D 1.55%. Okay, so this came in JEST 2014. Value of elastic constant for copper is about this much. Elastic constant. Okay, what is elastic constant? Newton per meter. Okay, and then the atomic spacing is this much. Okay. What is the amplitude of the vibration of copper atoms at 300 Kelvin as a percentage of the equilibrium separation? Okay, so your this one is your beta. This one is your A, atomic spacing A. This is a temperature T is given. Temperature T is given as a percentage of the equilibrium separation. So we know energy is half beta A square, half kx square. We can also write it as beta A square. Okay, beta A square. Sorry, amplitude square. Hmm. Here your A is given. Now in one dimension, here this is one dimension. One dimension, like kinetic energy is how much? Half kBt. Kinetic energy half kBt. Potential energy is also half kBt. Okay. So your total energy is what? Total energy is kb half kBt, that is kBt, which is equal to we know half beta a square. Okay, half beta a square. Alright. So what is the question again? As a percentage, okay. What is the amplitude of the vibration of this as a percentage of the equilibrium separation? Equilibrium separation. Hmm. What is the percentage? So let's see. Beta a square. So now A we need to find. So kBt, 2 kBt by beta is equal to A square. Now A will be what? Root over of 2 kBt by beta. Root over 2 kBt by beta. 2 into, so 2 into kb. What is the value of Boltzmann constant? 1.38 10 to the minus 23 into temperature 300 Kelvin given. Beta is how much? 100. And this is your root over. Right? This is your root over. So if you calculate this 600, 1.38 into 600, that is 828. So this will be 828 into 10 to the power minus 23 by 100. Okay, root over. Okay. So if you do it, 8.28 into 10 to the power 23 root over, and we cannot just leave it like 28, 82.3 10 to the minus 10 to the minus 24. Now we can calculate because this should be an even power. Okay, so A, if you calculate this, your A will be 9.09 into 10 to the minus 12 beta. Okay, which can be written as 0.009 nanometer, isn't it? I can write it like that. So what is the question? This amplitude is what percentage of the equilibrium separation? This amplitude of vibration of copper is what percentage of the equilibrium separation? Okay. So what is the equilibrium separation? The atomic spacing. The equilibrium separation is this one, 0.256. So 0.009 is what percent of 0.256? That is exactly the question. Nanometer, forget nanometer. So how to do it? Simple. 0.009. This is 09 also. I can write. Did you understand the question? 0.009 09 by 0.256 into 100, right? Hmm. So if you do it, you will get it as 3.5%. Please try to calculate on your own. Okay, you will get 3.5%, which is your option B. What it is asking again in the question, everything is given the amplitude. We need to find out amplitude, half beta a square. The amplitude is what percentage of the equilibrium separation, that is the atomic spacing. That much we need to find. Okay, it's a very good question. I hope you understood. Okay, next question. Question number 5. Okay. Question number 5. Okay, this is exactly the opposite question of one we did just in question number 3. If a proton were 10 times lighter, okay, so then the ground state energy of the electron in a hydrogen atom would have been. This one is homework for you. We just exactly did like this question number 3, less, more, the same. Option D, depends on the electron's mass. Okay, we did exactly this, the opposite of this question in question number 3. So you just do it in question number 5. Okay, next question, question number 6. A hydrogen atom in its ground state is collided with an electron of kinetic energy 13.377 eV. The minimum factor, the maximum factor by which the radius of the atom would increase is. The maximum factor by which the radius of the atom would increase is option A 7, option B 8, option C 49, option D 64. Hydrogen atom is a ground state is collided with an electron of kinetic energy this. The maximum factor by which the radius of the atom would increase is. Okay. See, 13.377. We know what is the ground state energy of like electron, hydrogen atom. Ground state energy is minus 13.6. Alright. So the thing is, how much will be added on minus 13.6, that we will get 13.377. So what can we do? Minus 13.6. How much can be added like to this? See, 13.6 minus 13 point, what is it? 377. 13.377. 13.3377. Subtract it. 3220. So 0.223 electron volt. If I add, okay, then the radius of the atom would increase. because hydrogen atom in its ground state with collided with the kinetic energy of this, the maximum factor by which radius of the atom would increase. That means this is the amount of energy that is required, right? This is the amount of energy. So which, can you tell me which state this energy belongs to? The E1 is this, E2 is minus 13.6 by 2 square, that is your minus 3.4, right? E3 is minus 13.6 by 3 square, that is minus 1.5. It will go on like this. So how to calculate this? So En is equal to minus 13.6 by n square is equal to 0.223. All right. So if we can get n, what can we get? We will get the state, like at which the radius of the atom would increase, right? So this will be how much? N square is equal to minus 13.6. This should be minus, okay? Minus energy, okay? Minus energy. Energy should be minus here, 0.223. So n square will be, if you calculate it, you will get it as 49 around. So n is actually 7. You will get it. N is equal to 7. Okay. So if, did I do any mistake? No. So n is your 7. So if n is 7, okay. So what is the radius? We know the radius formula Rn is equal to Bohr radius into n square. Okay. Bohr radius into n square, a square, n square. Because yeah. So question is maximum factor which radius of the atom would increase. At ground state, a radius of the atom was R naught, Bohr radius, sorry, A naught, right? A naught is the Bohr radius at the ground state. So how much it has increased? See, this is 7 square A naught. This is 49 A naught. So it was A naught. Now it is how much? 49 A naught. So how much it has increased? 49. Got it? This is the answer. Right? This is the answer. Alright. Next question. Right, next question number 7. It will be question number 7. Which of the following excited states, which of the following, which of the following excited states of a hydrogen atom, of a hydrogen atom, hydrogen atom has the highest lifetime, has the highest lifetime? Which of the, which of the following excited states of a hydrogen atom has the highest lifetime? All right. A is 2p, B is 2s, C is 3s, D is 3p. Okay. Which of the following excited states of a hydrogen atom has the highest lifetime? Okay. Try this question. This is a kind of a theoretical word. Like you need to know this. You can solve it. See, 2p and 3p. You can say these are called normal states. Normal states. Okay. So electron from 2p and 3p actually make transition to ground state within. You can write an electron from 2p 3p. Okay. Make transition to ground state, to ground state within, within 10 to the minus 9 second. Okay, but electron in 3s state like cannot come directly to ground state. Okay, it will come the 3s one cannot directly come to like ground state. It will come first, it can come to 1s. Okay, then it will come to 1s through 2p, 2p then 1s. 1s, like 3s to 2p to 1s, it cannot come directly to 1s. Okay, yeah. And but what is left then? 2s is left. So 2s is actually is called a metastable state. 2s is a metal stable state. Okay, so electron in 2s state actually what can make transition to 1s slowly, very slow transition to 1s, very slow transition. So that's why it takes a longer time. Okay, so 2s has, you can say 2s has longer, has long lifetime. These things you can only know if you read textbooks, right? Otherwise, these are not solvable. Like you cannot like see it and think that this will happen, this will happen. Okay. Okay. Next question. It's question number 7. Next question is question number 8. Which of the following statements? This is just 2000. Just 2015 now. We are going to just 2015. Okay, you can write down. Which of the following statements is true for the energies? Is true for the energies for the energies of the terms of the carbon of the terms of the carbon atoms in the ground state electronic configuration in the ground state electronic configuration 1s2 2s2 2p2. Okay, what is the ground state electronic configuration for this? Just write the options. 3p greater than 1d. Sorry, 3p less than 1d less than 1s. That means less than means the this one has the lowest energy. Sorry, this one has the lowest energy. It's saying that is the ground state energy term. It's saying. Okay, so from 1s to 2s to 2p2, you have to find the ground state. This is under Hund's rule. So I will explain. Don't worry. We have done this kind of questions before in our atomic physics like that playlist. It's there. Still, I will tell you again because this is a very important topic for any exam. 3p less than 1f less than 1d. Okay, so you can see 3p is everywhere. So then 3p is right, but we need to find the second one, isn't it? Okay. So here, what is the last state here? 2p2. So everything will be according to 2p2 then. Okay. Like the ground state will be decided according to 2p2. So 2p2 leave 2 like p2. That means 2 electrons, right? 2 electrons. So 2 electrons. If I write the like uh, um, L is summation ml. This is your plus 1, 0, minus 1. So your L is plus 1. Okay. S is what? Del ms. That is half, half. There's only two halves here, and there is nothing here. So half, half. So S is your 1. L is 1, S is 1. What are the J values? L plus S 2, L minus S. So 1 plus 1, 2, 1 minus 1. That is 2, 1, 0. Okay. Now J is 210. S is 1. That means 2s plus 1 value is what? How do we write a spectroscopic term? 2s plus 1 L J, like this. So 2s plus 1 is 2 into 1 plus 1, that is 3. L is 1. For L1, what is this thing? S P D F. L is 0, 1, 2, 3. So L should be P. J is 0, 1, 2. Okay, now this orbit is half less than half filled. Less than half filled. So according to Horn's rule, if it is less than half filled, then the lowest J value will have the lowest energy. Okay, lowest J value will have the lowest energy. If it was more than half filled, then more than half filled, like P4 or something, P5, more than half filled, then highest J value will have the lowest energy. Highest J value will have the lowest energy. So here lowest J value, that is 0. So 3p0 is the ground state. That is, so we know it's in the options. Okay. Then okay uh, then what is there in the second one? 1D, 1S, 1F, 1F. So here what is the answer? Can you tell me? Here what is the new one? Next lowest two. What is the lowest? Here. See, now what? Now what? How to do now? Now P is gone. What is left? D and S. D and S. And if you see D and S, there is 1 and 1. Okay. So if both have the same multiplicity 1, 1, so the one with the highest like L value will be the lowest energy. So 1, 1, which is the highest L value? D. D has a L value 2. So D should be lower than S. So this should be the option. Got it? This cannot be the option here because S is lower than D. So D is the highest one. So D should be the option. Is that all right? Needs on. Okay. Question number it was. Question number 8. Question number 9. Question number 9. The H2 molecule. The H2 molecule has a reduced mass. Has a reduced mass. M is equal to 8.35 into 10 to the minus 28 kg, and an equilibrium internuclear distance r is equal to 0.742 10 to the minus 10 meter. The rotational energy in terms of the rotational number J is rotational energy in terms of the rotational number J is E rotational J is equal to 7 J whole into J minus 1 MeV E rotational J is equal to 5 by 2 J plus 1 MeV. E rotational J is equal to 7J whole into J plus 1 MeV, and E rotational J is equal to 5 by 2 J whole into J minus 1 MeV. Is that alright? This is from JEST 2016. Okay, try this question. Try this question first. The ST molecule has a reduced mass m is equal to this and equilibrium internuclear distance r is equal to this. The rotational energy in terms of the rotation number J is, okay. The ST molecule has a reduced mass this and equilibrium internuclear distance this. This is one of the easiest questions. Like mass is given, r is given, J is asked. When like we know E rotational is h cut square by 2I J whole into J plus 1. I is your what, mu r square. Isn't it? Mass is given, reduced mass is directly given 8.35 into 10 to the power minus 28 into r square. R square is what, 0.742 into 10 to the power minus 10 square. Okay. So from here you can calculate I and you can just put it here. Okay, you can just put it here. And the rotational energy in terms of rotational and quantum. Okay, that's it. I think this much only. You just have to put it here. H cut. H cut is what? H cut is how much? 1.34. Sorry, 1.04 into 10 to minus 34. Just put it there. So 1.04 into 10 to the minus 34 square divided by this one, 2 into this one, into j whole into j plus 1. You will get your answer. Okay. Very direct question. I hope you can solve it easily. Question number 9 gone. Question number 10. This one just 2015. Question number 10. If the Rydberg constant, if the Rydberg constant of an atom, if the Rydberg constant of an atom of finite nuclear mass of finite nuclear mass A finite nuclear mass is alpha r infinite. Okay, where r infinite is the Rydberg constant. R infinity is the Rydberg constant corresponding to the corresponding to the corresponding to an infinite nuclear mass corresponding to an infinite nuclear mass. Okay, the ratio of the electronic to the ratio of the electronic to uh, nuclear mass of the mass of the atom is. This is the question. The Rydberg constant of an atom of finite nuclear mass is alpha r infinite, where r infinite is the constant, Rydberg constant, corresponding to an infinite nuclear mass. The ratio of the electronic to nuclear mass of the atom is. Ratio of the electronic to nuclear mass of the atom is. That's the question. Okay. Ratio of electronic to nuclear mass of the atom. So R mass, R of any mass is R infinite by 1 by me by m. That's the formula. Okay. So here Rm is given as alpha R infinite, isn't it? Alpha R infinite is equal to R infinite by 1 plus me by m, isn't it? So this is what you are asked. Me by m, electronic mass by nuclear mass. Me by m. Okay, me by m is asked. Infinite R infinite cancelled. So alpha is equal to 1 by 1 plus me by m. So 1 plus me by m is equal to 1 by alpha. So me by m is equal to 1 by alpha minus 1, which is 1 minus alpha by alpha. This is a what? This is a electronic by nuclear mass. 1 minus alpha by alpha. Okay, I hope you understood. This was just 2017, I think. Sorry, just 2017 or something. Okay. Next question. It was question number 10. Question number 11. Question number 11. Consider a hypothetical world. Consider a hypothetical world in which the electron had spin has spin 3 by 2 instead of 1 by 2. Instead of 1 by 2. What will be the electronic configuration? What will be the electronic configuration for an element with atomic number z is equal to with atomic number z is equal to 5? Consider a hypothetical wall in which electron has 3 by 2 instead of 1 by 2. What will be the electronic configuration for an element with atomic number z is equal to 5? Okay. So 1s4, 2s1, 1s4, 2s2, 2p1, 1s5. Option D, 1s3, 2s1, 2p1. Okay. Here, hypothetical world in which electron has spin 3 by 2 instead of 1 by 2. So if electron has spin 1 by 2, what happens? So 2s plus 1, that is the rule. So 2 into half plus 1, that is 2. So 2 electrons should be there in 1s. Clear? Isn't it clear? So if like in this world we have s is equal to 3 by 2. So the 2s plus 1 will be what? 2 into 3 by 2 plus 1, that is 3 plus 1, that is 4. So 1 is 4. Z is equal to how much? Z is equal to 5. Atomic number 5. 4 electrons are already there in 1s. So how many electrons are left? 1. So after 1s, what is there? 1p. So 1 is 4, 1p. Sorry, 1 is 4, sorry, 2 is 1. That is a nuclear configuration. I'm really sorry. This is your like atomic one. 1 is 4, 2 is. I did this. 1 is 1 is half, 2p, 3 by 2. That way I did. I'm sorry. 1 is 4, 2 is 1. Okay. So the option A is correct. All right. This came in JEST 2018. Okay. So JEST 2019. This came in JEST 2019. Okay. Another question. This will be the last question. Number 12. What is the difference between what is the difference between the maximum and minimum eigenvalues of a system of two electrons whose Hamiltonian is whose Hamiltonian is H is equal to J S1 dot S2. Okay, where S1 and S2 are where S1 and S2 are the corresponding S1 and S2 are the where S1 and S2 are the corresponding corresponding spin angular momentum spin angular corresponding spin angular momentum operators of the two electrons, spin angular momentum operators of the two electrons. Okay. Option A, is J by 4. Option B is J by 2. Option C is 3J by 4. Option D is J. Okay. Let's try this question. Let's try this question. So what is the difference between the maximum minimum eigenvalues of a system of two electrons whose Hamiltonian is J is equal sorry H is equal to Js dot S1 dot S2, where S1 and S2 are the corresponding spin angular momenta operators of the two electrons. Okay, so we know your PDF is also over. Okay, we know what do we know? H is equal to J S1 dot S2. So can be written as J what? Okay. S is equal to what? S can be written as S1 plus S2, isn't it? So S square is equal to S1 square plus S2 square plus 2 S1 dot S2. So 2 S1 dot S2 is how much? S square minus S1 square minus S2 square. So S1 dot S2 is how much? S1 dot S2 is S square minus S1 square minus S2 square by 2. Okay. So we'll just put it there. So H is equal to J S square minus S1 square minus S2 square whole divided by 2. Now S is how much? S is your S whole into S plus 1 H cut square. Okay. Minus S1 whole into S1 plus 1 H cut square minus S2 whole into S2 plus 1 H cut square whole divided by 2. Yeah. So we know S1 is half, 2 electrons, S1 is half, S2 is half. So we'll just put it there. But S values are half plus half and half minus half. That is 0 and 1. So J whole into first S is equal to 1. 1 whole into 1 plus 1 minus half whole into half plus 1 minus half whole into half plus 1 h cut square whole divided by 2. Okay, if you calculate this, that will be 2 minus 3 by 4 minus 3 by 4 h cut square by 2. Okay, so this is how much? 4, this is 8 minus 6, 2 h cut square by 2. So that is h cut square by 4. And if you write the h, that is j h cut square by 4. Okay, so this is for s is equal to 1. For, okay, this is for h is equal to 1. That is maximum value. You can also calculate for s is equal to 0. Exactly same thing. Here it will be 0 minus 3 by 4 minus 3 by 4 h cut square by 2. That will be what? Minus 3 by 4 h cut square. And h will be what? H minimum will be minus 3 by g. Why I did it very rush, like hastily? Because we have done it before. Exact same question we have done it before. So I hope you can do it yourself. Alright. Exact this question we have done it before. Just have to take, see, you just have to take for s is equal to 0, you have to put the formula h is equal to what? J s whole into s plus 1 minus s1 whole into s plus 1 minus s2 whole into s plus 1 by 2 h cut square. So s is equal to 0, put s is equal to 0, that will be your minimum value. Put s is equal to 1, that will be your maximum value of h. That is the question, isn't it? Okay, what is the difference between them? Okay, the max. Okay, what is the maximum value? Maximum value is h max is j h cut square by 4. H mean we got as minus 3 j h cut square by 4. So the difference del h is how much? J h cut square by 4 minus minus plus 3 j h cut square by 4. Okay, so if you take the LCM, 1 plus 3 jh cut square, that is 4 by 4, that is 1. So jh cut square is the answer. Okay, so the answer will be jh cut. So that means j in terms of h cut square, if if they have taken h cut square as 1, so the answer is 1 j. Is that all right? I hope you understood. I hope you understood. Okay. Okay, then these are the questions from 2012 to 2019. So I hope you understood. and from 2020 to 2023 we'll solve in the next session. Okay, till then, thank you very much. Stay tuned to the channel.